Hello, my name is Aaron Tucker from the Earl E. Bakken Medical Devices Center at the University of Minnesota. Today, I will be presenting about the design and implementation of a balloon catheter pressure testing system. Medical device companies that aim to sell catheters with pressure sensing elements need a way to test their systems before packaging their product. An example of one of these products is an intra-aortic balloon pump, which provides mechanical pumping assistance to a patient experiencing cardiogenic shock. To test these devices, companies will place the assembly in a controlled pressure chamber to test the response to pressure changes. However, commercially available systems are cost prohibitive. Additionally, current products have slow settling times, which makes it difficult to test rapidly changing pressures. There is a need for a controllable, low-cost, low-pressure system for pressure sensing balloon catheter testing. In order to address this need for a low-cost catheter testing system, a pneumatic chamber was built with a custom program used to alternate pressure in a similar manner to the human body. Before designing the controller, several important steps were taken to ensure proper design principles. First, the physical system was built so the controller could be designed using system identification. In this process, data is taken from a basic system test and used in the modeling process to provide accurate model parameters. This system was built using mostly off-the-shelf components and cost less than $500. The main components include an air storage tank in which air drawn directly from a lab air supply is stored in this tank before being transferred to the test chamber, a custom test chamber which has been designed to fit balloon catheters, a dual Arduino control module, in which two Arduino microcontrollers work in tandem to control the solenoid valves and monitor sensors. Second, since pneumatic systems exhibit nonlinear behavior, the system was converted from a fluidic model to an electrical circuit model to achieve linear approximation. In this analogy, the resistors represent the solenoid valves to use to control flow, the capacitors represent the air storage tank and the test chamber, and the voltage represents a pressure differential. As you can see, this system can be depicted as a set of resistor-capacitor, or RC, circuits in series. From this model, a linear state space realization of the circuit analogy was used as the framework to control the pressure of the system. Third, a set of specifications was developed in order to provide parameters for controller design with the average behavior of a human cardiovascular system in mind. These specifications were used extensively in controller design and refinement. After these steps were taken, a feedback controller was designed to simulate the pressure profile experienced in the human body. Since a single RC circuit is a simple single input, single output system, the serial RC system was split into two loops to optimize Arduino computation. In order to find the time constants of the two loops, system identification was performed to analyze behavior. A step input was applied to each loop, and the pressure data was logged via the Arduinos. This collected data allowed for empirical determination of the system characteristics. The electrical circuit analogy was used to produce the state space model of the pressure system shown in equations 1 and 2. Using MATLAB, a proportional integral controller is designed and implemented for each loop. The specifications previously developed were used to tune the controller gains and parameters. This controller was then converted to a digital format and programmed into the control module. In order to evaluate the control algorithm design, we created a series of tests based on the design specifications. By measuring the chamber pressure and comparing to the input, the system was evaluated for its ability to track a reference command. The system remained stable for oscillations ranging from 0.8 to 2 Hz, which accounts for a wide range of heartbeat rates. The system was also evaluated over several trials to examine repeatability. Additionally, this chamber safety valve was opened during one test to simulate the disturbance. Finally, a balloon catheter was inserted in the chamber and inflated to examine how the system behaves in an actual test setting. Errors experienced in reference tracking are due to two factors: linear approximation of nonlinear behavior and low-cost components. Since a primary goal of this system was to reduce cost, we determined that some system error was an acceptable trade-off for a versatile test platform. Furthermore, the system characteristics produce significant improvements over the commercial systems in terms of cycling time and settling time. In conclusion, we believe the novel method of converting a nonlinear fluidic model to a linear electrical model allowed low-cost components to be used in an efficient way. Subsequently, we believe this system provides an effective alternative to current test platforms available on the market. With that, we offer our thanks for your participation in DMD 2020 and our thanks for watching.